Okay, back here with some examples from ALEKS. And well, obviously, if you clicked on this video, you saw the title, which was talking about counting principles or some variation of that phrase. And, ultimately, what we're doing is literally just counting the number of possibilities that can uh, happen, when you do some sort of experiment or, probability experiment or scenario. So here we have a fairly simple one. And, again, I'll kind of get into why we're doing that. But the quick answer to the question, why are we doing that, is ultimately we're going to use these counting principles to compute theoretical or classical probabilities. And so with this example, I'll summarize that at the end of this example here. So, we have a spinner. Kind of imagine a big circle here. I don't have a picture of one. I'll just use my mouse here. And then half of it, down, there's a line completely down the middle of the circle here. And then one half's colored, say red, and it's labeled A, and the other is blue, labeled B, or, whatever color you want. But we spin that spinner. And so there are, again, two different outcomes, right? It can land on the A region or the B region, okay? So there's two different outcomes there. Then after the spinner that spinner spun, there's another spinner that has 5 sections. So imagine, again, the circle evenly divided into 5 sections here. Actually, it doesn't have to be equal. We'll get into that later, but say there's 5 sections and we spin the other one and it can land on 1, 2, 3, or 4, or 5. Okay, so what we're really doing here is counting all the possibilities when we spin the first spinner and the second spinner. So one of the outcomes would be, well, the first one lands A and the second one lands 1. First one lands A, the second one lands 2. And you get the idea here without going through all of those. And so therefore, I can count up the number of possibilities that, of these events, or all possible events, I should say, that can occur when I spin that spinner. So you'll be asked some questions kind of like this, because ultimately, let's say we want to know if we get first spinner A and the second spinner 1. Well, there's only one of those outcomes right here, okay? And if all these are equally likely, in other words, if this spinner was, had 5 equal sections for 1, 2, 3, 4, and 5, and this one had equal sections or areas, whatever term you want to use for the first spinner, then what we can say is, well, the probability that happened is 1 out of all of these, which I believe there are 10, okay? And so, by counting all these using a tree, essentially that's what using a tree diagram does, is just maps all the possible outcomes, okay, and gives you some kind of a visual aid there to go ahead and do that. And therefore, I'm just going to click the solve button to fill these in real quick, and explain them. But, we mentioned here there are 10 possible outcomes. And now how many outcomes involve landing A on an even number? Well, again, all we need to do is go down and look at all the A's, and here's one of them here with the 2 and the 4. Obviously, 1, 3, 5 are odd numbers, so there's only 2 of those. And then how many outcomes landing on the number other than 4? Well, again, by examining all the possible outcomes here, you can see that there are 2 4s times we can get 4, one right here and one right here. So, we counted up all the other ones or subtracted, that's 2 from 10, we're going to get 8 either way. All right. So the terminology that you came across, and you will here, is, the sample space. That's the list of all possible outcomes. And then our desired outcomes, depending on what we're asked to find here, becomes a way of determining probabilities. So again, if we want the probability of getting an A on the first spinner and a 3 on the second one, again, we just take count the sample space, all possible things. That's the denominator, 10, writing in space here, and then we list the number of desired outcomes here, where we have just the 1, and divide it by 10, and So we would say 1 out of 10 or 10% and so forth. Okay. So that kind of gives a little bit of background where we're going here with this. And so again, we're just talking about ways of counting these up. Now, I'm going to come back to this problem again, but just remember there are 2 outcomes for the first spinner and 5 outcomes for the second. And there's a little quicker way of doing that, and that is the the counting principle here, where we are going to basically use this idea of multiplying. Okay, so essentially, if I would, actually, if I go back here, I can get to 10 here. Let me see. Okay, so we got one here with 2 and 6, but again, I could list them all out using the tree, but I could quickly get these if there are 2 outcomes here and 6 on the second one, right, with the number cube. If I just multiply 2 times 6, I'm going to get 12 very easily here for the 12 outcomes, and I wouldn't have to list all this. So it's kind of like a quick way of finding these without going through the whole tree, because you'll see later on some of these trees can get pretty complex, and it would take a huge amount of time and effort to go ahead and write out the tree like we have here. And so we'll resort to the counting principle, which is basically just using that multiplication rule that I just had here. So so again, if I go here and just exposing the answer here real quick, and I'll explain it, because that's all you're typing into ALEKS 12. But it says here, Teresa must choose a shirt, a pair of jeans, and a cap for today's outfit. So if she has 2 different shirts, 2 different pairs of pants, and 3 caps to choose from, I could go ahead here and write out a tree and say, okay, shirt 1 and shirt 2, and then off of shirt 1 and shirt 2, I can go with the 2 pairs of pants, and I would have branches coming off that way. And then off of each of those branches, I would have 3 caps, and that would give me endpoints or listings of all the possible combinations or outcomes, if you will. Well, again, if I'm just asked to find out how many there are, instead of writing out, taking the time for that tree over here to write that out, I'm just going to take 2 times 2, which is 4 times 3, which is 12. So pretty simple way of, again, doing that. Now, remember, I introduced that last time, or on the last example. They did want the tree because they asked some other types of questions. But if it's simple like this, again, just determining the number of different outfits, you're not listing the sample space, all the different outcomes. All you're doing is counting up how many different outcomes there are. So if we replace the word outfits with outcomes, we get the idea in terms of the general sense. There are going to be some situations here now where we can kind of repeat. And so it says supermarket wants to send codes for 25 cents off a bag of chips. Each coupon code will have a 1 digit followed by 4 letters. So the letters D and E and the digits 0, 5, and 8 will not be used. So there are basically 24 letters and 7 digits that can be used. Okay. So now remember, we have 1 digit and 4 letters. So I'm going to jump in the explanation here, and again, just show you where this is coming from. But I'll put the solve in here. Notice we have over 2 million of those, which is quite a bit of, excuse me here, outcomes. Okay, so that's a lot. And again, you're talking about, reward, programs or whatever, and these things that they're putting out there, they've got to have a lot of them. And so what we'll do is I'm going to look at the explanation so you can understand. I think there's a visual here that makes a lot more sense. So if I get into here, okay, the coupon has 1 digit followed by 4 letters. Because we can repeat those letters, in other words, it's not like taking a pair of pants and wearing those. You can't wear 2 pairs of pants at one time like the other examples. We can actually have repeats here. So if I just took 7 times 24, for the first letter times 24 times 24 times 24. Here you have, they wrote it out here. That's where the 2,322,432 is coming from. Okay. So that's how many different codes can be generated. And, for whatever reason, they're excluding D and E here and 0, 5, and 8, probably just to get some variety for these homework questions. So, obviously, you may have a scenario in your example or question that you have to do where they might be excluding or, more letters than that, or even no letters. So it just depends on, the variety that they're going to present to you. Okay. But this is a nice feature, going and taking a look at the explanation. It won't give you credit now if you answer that. So you have to go to try another. And you can see that if I got into that, now they're excluding 4 letters here. And also they're excluding 4 numbers. Okay. So you get the ID here, and we're dealing with a license plate with 4 letters and 2 digits. So again, you can apply that principle just like we did earlier. Okay, so that would count for, ones with repetition. Now, I'm not going to get into everything here. I'm going to kind of, I don't have time to do every single type of problem, but what we want to do is take a look at what permutations and combinations are. And when we do that, I'm going to just click on that problem here. And what we see here is just this notation with a C and a P. Now, these formulas here you can use them. And, if you kind of scroll down here, it should be somewhere down here. Here we go. Here's the one for permutations, and here's the one for combinations. And they give a designation of what these things represent. So, the number of permutations of n objects taking r at a time, that is the number of ordered, and this is where order is important here, okay? We can use this formula. So in other words, like if we had 10 people running a race and we want to know how many ways that the top 3 can finish out of those 10 people, how many different ways that, we can have 3 people finish the race in first, second, and third. Order is important. Then we would have a 10 here and a 3 over here. If we're not concerned about, let's say if we were saying, oh, we're just concerned about how many different combinations we can get of people in the top 3, where order is not important, then we're going to use this formula here, okay, where we have an N and an R. So that would be the 10 people and 3 here. And notice the formulas are very simple, except we're just dividing by another R factorial. And by the way, factorial, if you remember, I don't know if they have that up here or not. I don't think they do. Might be below. No, they don't. Okay. So for instance, like 2 factorial here, and I'll just go into this calculator. And by the way, if you have a graphing calculator, TI-84 does it. For some reason, my TI-84 emulator is not working, so I'll use the 89. But this is, again, found on this website. It's pretty good calculator. But if you go to the math menu here by pressing second 5, and then they have a probability menu in there for doing probability computations, you can see that we have this here. So if I did for instance, the 10 racers and the top 3, okay, so if I select this and I just put the 10 in the comma with the 3, it's going to give me, this is how many different ways they can finish. First, second, and third, where order counts, there would be 720 of those. However, if I was just interested in the combinations, again, I just go to my probability menu again, selecting 7, I go down to NCR, okay, which is, again, order doesn't matter here. And I put in the 10 and 3 again for the same scenario, except I'm excluding order here, and I get 120, okay? If I do look at the math menu here, and again, I usually use the TI-84. Let me just go down here and see if that, yes. Okay, so here is the exclamation point, so to speak, okay? So if I, put that here, I actually should have a number in front of it. And what what 3 factorial would be equivalent to is 1 times 2 times 3. So we can do that one in our head. 1 times 2 times 3 is obviously equal to 6. So if I went to 4 factorial, it's going to be 1 times 2 times 3 times 4, which is equal to 24. So we'll just, again, verify that that works. And sometimes, instead of going back to the menus, you can do cute stuff like this, where we just go and, up here, skip hitting, and it'll recall that last command. And then I could, do something like I could go back over this and then insert a 4, just to save some time. Or you can go back through the menu. It doesn't really matter which way you do that. But so if let me see, get back to my ALEKS window here. That's where these formulas, I don't want to get too bogged down into it, but, again, just know when to use which formula. And the easiest way to use these formulas, you can do this on your calculator. Most of you should have a scientific calculator, and you'll see an exclamation point somewhere. It might be in some menu somewhere. It might be on your keypad. It might be, one you have to press a second button first, or a function button or something like that. You can type these out in your calculator. I would recommend, since this is an online course, use the tools that you have. And, again, going into this math menu here is probably going to be the easiest way of doing that. Just going down to the probability menu, and then you can see that, those 3 things are right here that you're going to be using here for some of these problems. Okay. So if I, go back to, let's see, that was the formulas here. Okay. So if I just, again, let me just do this one, 9, I'll solve this. This one's 84, where we have 9 and 6. And again, maybe I'll do the shortcut method here. If I just escape out of these, and, I can actually go over here and, oh, wait, no, I wanted this one. I thought we said we would select 9 and 4. I got to get that 4 out of here. That's where you got to be careful doing this. And I think we said there was a 9 and a 4. So I'll go ahead and put my 9 and my 4 in, and I want to get this out of here also. Sometimes when I click with, sometimes it's not worth using the technique I just did there. But there's your 126, okay, with the 9 and the 4. And I did the wrong problem. It should be a 9 and a 6. So if I go back here again, I think you get the idea, but I'll just go ahead and do it again. 9 and 6, since we're already here. There's your 84, and there's your 84. Okay, so the calculator is going to be a lot easier to do it. It probably would have been best just going into the menu instead of trying to edit a former command, but oh well. Okay, and all right, so let me go back here, and for some of this stuff here, if we go to different permutations and combinations, if I get into one of these problems right here, again, this is just going to be a matter of picking the right formula to use. And this is again, suppose we want to choose 5 letters without replacement from 9 distinct letters. Okay, so again, if I would just try to streamline this quickly, go into this, we could refer to the formulas and know which one to apply here, but you could see that in my part A here, because I'm not replacing here, okay, and we're talking about how many ways of choosing letters, even though they don't say order matters, okay, they're implying the way the question is worded, okay, in terms of, from the 9 letters, if the order of the choices, they do say is taken into consideration. So we know we're using permutations there, and you can see that that's the technique they're using. However, in question B, they're asked how many ways they're choosing 5 letters without replacement. if from the 9 letters if the order of the choice is not taken into consideration. So, here, if we go back to the question, I guess the key part of the phrase in this is where we say if the order of the choices is taken into consideration, or if the order of the choices is not. Okay, so this tells you you're using combinations. This tells you you're using permutations. Okay, so you're going to have some other questions like that here. Some might be a little bit more in terms of, I can go through all of these, but in terms of context, okay, and they may switch around and give you different scenarios, but they're all going to boil down to something along the lines again of, here there's 16 appetizers. From here you're choosing 12 from the party. How many are possible here? Does order really matter when you're having appetizers? And again, it says a company here have 3 colors to improve or to include in its promotional mini box of 3 crayons. And it says company can choose 3 mini box colors from its collection of 70. How many mini boxes are possible? Okay, so now we're having, from 70 here, they're distinct. And so that would tell me that order is kind of implied here, just because they don't actually use the phrases. But, we'll go ahead and check it out here again. You could see that the first one here, we're using combinations because it really doesn't matter what order you eat your appetizers in, whereas here that box, that 70, was distinct. So we can look at that as order being implied or implied. Okay, so I know this is these videos kind of drag on a little bit, but I tried to create a group of problems that were somewhat similar in nature. All of these things involve counting. Okay, and we'll get into some now when we start talking about, again, computing the probabilities, and we may have to resort to some of these counting methods to do so. But if you look at that group of problems here, those all involve counting. So I'm going to stop this video now, and I will get on with the next one.